Hello everyone, and welcome to this quick demonstration on how to use the OpShin toolchain to write smart contracts and make them better. OpShin, you might have heard about it, lets you write smart contracts in Python, but it provides more. It integrates frictionlessly with PyCardano, an off-chain library. It provides benchmarking and testing frameworks, called the Plutus bench, and generic optimization libraries such as the Plutus CLI. There's also more to it, but you can explore the GitHub repository if you're interested. We are gonna write a smart contract today in OpShin. Let me quickly recap how Python syntax works. First of all, we can import parts that we wrote in another script using import statements. We can define functions with type annotations. This is a parameter type, this is a return type. We can assign variables. We can have control flow using if and else. We can reassign variables, also augmenting them. For example, this is equal to b equals b plus a. We can loop over variables. We can trace using print. We can use assert statements to check that a certain condition holds. This is useful if you want to make a validator fail. We can define classes with attributes, typed attributes, initialize them by calling them, and also having attribute access and indexing into lists and strings. So without further ado, let's start writing a contract. For this demonstration, I'm using the PyCharm IDE, but there are plenty of IDEs that support Python, and OpShin is a strict subset of valid Python. All OpShin contracts are actually Python contracts, programs. So you can just use any IDE, for example Visual Studio Code. To install OpShin, first make sure that you have the right Python version. I'm gonna do this and check Python 3 minus version to check that we have Python 3.10, which is compatible. Now I'm gonna do pip install OpShin. This will download all the dependencies and set up the program. To write a contract, I'm just gonna create a new Python file. I'm gonna call it mycontract.py. Generally, in the first place, you'll want to import the prelude. This will give you a lot of handy definitions, such as the ledger definition. Now we're gonna define the validator. As you know, a validator in Cardano is a function that takes several arguments. We're gonna define a function called validator. This name is fixed. If you want your contract, you have to name your function validator. And this will take, because we are writing a spanning validator, it's gonna take 3 parameters. The first one is the datum. The type of the datum doesn't matter here, so we're gonna just assign it the anything type annotation. The redeemer is also anything, and we have the script context, which is of type script context. The return value of our contract is none. Note that OpShin validators are not similar to Plutus validators in that they return a Boolean value. OpShin validators are more like Unix programs. They either pass or they fail with an exit code. So if you want your program to fail, you're gonna do an assert or make some operation that fails. But if the program returns something, and it doesn't really matter what it returns, then the validator will approve the transaction. What we have written now is a contract that you already know. It's the always true contract. This validator will always pass. The pass will just not do anything. We can also return none, which is the same. This contract will always validate and never fail. The opposite would be assert false and some error message. This contract will never validate. This is always false. Now, let's check how to build this contract. Let's see how to build this contract. For this, we go back to the terminal and write opshin build mycontract.py. This will generate a few build artifacts into the folder build. Subfolder mycontract, because that's the name of our contract. Contains the address on the mainnet and the address on the testnet. Contains a Plutus file which you can use with the Cardano CLI, and it contains a CBOW script, which you can use with PyCardano or Lucid. It also contains a policy ID in case you want to write a minting policy, which we're not going to do today. We will be interested in the address, but it doesn't matter right now. In order to write the resting contract, we're going to have to make a few assumptions about who can withdraw funds from our address. We're going to start with making the datum a pubkey hash. So if you send funds to an address, to our validator, you will attach the pubkey hash of the person that is supposed to redeem the funds. We want to make sure that somehow the datum has signed the transaction. So the owner of that datum, of that pubkey hash, the private hash for this pubkey hash, has signed the transaction. And how do we know this? Well, we can look in the redeemer, but we'll look in the script context. So let's explore how the script context looks. It's built of txinfo and purpose, and inside the txinfo we find some interesting information about the transaction that wants to withdraw the funds. For example, a list of signatories. This is a list of pubkey hashes, so we can just check for signers in our context txinfo signatories. If datum is the signer, this is actually a signer, not the signers, then we're gonna say, okay, this is actually fine. And if this is not true for anything, then we'll set the result to false. So we're gonna loop over the signatories. If any of the signatories is the same, then we're gonna set this to true. And then we're gonna assert that the result is true. Let's try to build this. Okay, that worked. For the vesting contract, we also want to make sure that a user cannot withdraw the funds before a certain deadline. Now, the deadline will not fit also into this pubkey hash, so we're gonna create a bit more complex datum. We're gonna generate it like this. We define a data class called the class vesting parameters, and it inherits from Plutus data. This is just formality, and it will always look like this if you define a datum. Now, there is a beneficiary which is supposed to receive the funds from our address, and there's a deadline which is of type POSIX time. If you look at POSIX time, it's really just an integer. This is gonna be Unix epoch time. And now the datum for our contract is not the pubkey hash alone, but it's the complex vesting parameters, which contains both variables. Let's try to build this. And we're gonna see that there's an error. We cannot compare the datum with a signer because the datum is now of type vesting parameters and signer is of type bytes. Instead, we should access datum.beneficiary, which is the new signer. Try to build this, and it works. Now let's make use of that deadline. The deadline is a specific point in time after which we can withdraw the funds. How do we know what time our transaction is valid? I'm going to look in the script context, transaction info, valid range. This has a lower bound and an upper bound, which is the time when the transaction can first be submitted and the time when the transaction can last be submitted. And we're going to make sure that the transaction can first be submitted after the deadline has passed. For this, we're going to import a bit more utils. So from OpShin, we're going to import the ledger interval library. This contains a very useful function for us, which is called contains and make from. So what we're going to do is define a time frame that starts at datum.deadline and ends at positive infinity. So it's from deadline to infinity, and we want to make sure that the valid range of our transaction is inside this range. So context.txinfo.validRange should be inside of the interval from deadline to infinity. So to make sure that this holds and the signatory has signed, we're gonna just add this in the next line and assert that it's true. Otherwise, we can say the transaction was sent too early. Also, this error message can be improved. We're gonna say the beneficiary did not sign the transaction. Let's try to compile this. And it worked. Great. Let's try to deploy this contract on-chain. To deploy this contract on-chain, there is a repository called OpShin starter-kit, where you will find a few additional utilities as well as the off-chain code to deploy this contract. As you can see, I've copied the contract over into this repository. In the OpShin starter-kit, we're gonna first also build the contract again. I'm gonna just call Python 3 scripts build to generate the contract, now with a different name. We can also use the script here to generate some public keys, so we can actually try to use this. And I've already created an owner pub key and a beneficiary pub key. Let's have a look how to interact with this contract. First, we're gonna have a look into MakeVest. MakeVest creates the vesting output, so it will generate the correct datum and send it to the validator address. One interesting thing you see here is that it's possible to import the vesting contract. And why we do this, you will see in a second. This utility was built as a CLI, so we can call it in a second just with some interesting arguments. It interacts with Ogmios, but also can use Blockfrost. It loads the payment address using our utilities. And now we create the datum that we send to the contract just by involving the definition, the very definition used in the contract. So this is the vesting params. It also resolves to our contract. And we can set the beneficiary and deadline values to the values that we want to have. Then we load the address from our build, the testnet address, and generate a transaction builder with an input address, an output address, where we attach to the script address specified amount and the datum that we generated from the on-chain definition. Sign the transaction and submit it. Let's give it a try. So I will call the MakeVest, send from the owner address with a beneficiary pubkey hash, send 5 ADA and wait for 20 seconds. Make sure, if you call this, that you have an Ogmios instance connected with the right parameters. You can run this easily using Demeter run. I have one Ogmios instance here that is connected to the preview testnet. As you can see, we now have submitted the transaction. We might not be able to see it on Cardano Scan yet, because it will take a few seconds to arrive on chain. But in the meanwhile, we're gonna have a look at the collection code. To collect, again, we import the vesting contract. And now we just specify who wants to collect their funds. We can load the script using the script seaboard that we generated during building, and generate a Plutus v2 script from it, and then an address. To find as output we want to spend from the vesting contract, we can now just iterate over all the UTXOs at our script address and check if there's a datum attached to them. And if there's such a datum, we can just try to parse it using our on-chain definition from the seaboard that's actually on-chain. So on-chain you will never find the actual type, but in this case, because we have the on-chain definition able to be parsed from a seaboard bytes, we can just take the datum seaboard, parse it into the format of our on-chain definition. And then we have an object where we can access the attributes, can check if the beneficiary is right, can check if the deadline is right. And if we found something that we can spend, then we want to spend this transaction. So in this case, the beneficiary is what we specified as the receiver, and the deadline of the transaction is before our current time. We're gonna set a collateral as well, generate a redeemer. We recall that the redeemer value is really not interesting here, so let's just put a 0 there. Then again, transaction builder, add a script input, the UTXO we found with the right datum, add the script that we loaded, add the redeemer, add a collateral. Now we specify that our user has to sign so that its signature will turn up in the transaction script context signatories. We're going to specify the validity of our transaction, and then we'll submit this transaction to the chain. Let's try to run this. While this is submitting, let's have a look at the transaction that we sent to the chain. Yes, we can see it by now. And we can see that it was sent to this address, which is a contract address. And we can see that this address has a datum attached. And this, if you know a bit about the JSON notation for contracts datums, then you will see that this looks fine. But essentially, if you use PyCardano to do all of this, you don't really have to worry about the presentation on chain. You will just parse using your definition from the contract. Neat. Now we collected the vested money from the contract address. We can have a look on chain. We can see that there's a transaction. This is the transaction we had with the datum, and the contract that we used was involved with a redeemer spend and a collateral involved. So yeah, this was just very easily generated by the PyCardano off-chain code. Let's talk a bit about optimizations. When writing smart contracts, especially larger ones, you might find yourself in a position where the contract is too large to fit in a single transaction, or maybe several contracts don't fit in a single transaction anymore, or the script execution units are used up. And for this, OpShin also provides a general purpose tool. So the tool is called Plutonomy CLI, and let's have a look. It's a command line interface. You can just run it like this. And what it does is you pass it the CBOR file of a contract and tell it how to optimize it, and then it will generate a new CBOR file. The CBOR is just a bytes representation of your contract. And if we have a look at build my contract, we will see that this is already quite large. It's 13,000 digits, which is 7 kilobytes. Now we can run Plutonomy CLI build my contract script CBOR. We're gonna optimize it with the default optimizations, which will preserve all the semantics and keep the debugging traces so that it's still easy to read the contract. Aggressive would remove the debugging traces, which is a bit inconvenient. So let's just default optimize and write into script optimize.cbor. And we see that we just got 50% off. And yes, so we see it's just 6,000 digits, 3 kilobytes anymore. And now you might want to have the Plutus and policy ID and everything from this. For this, we will use uplc, which is a package that's also part of the OpShin toolchain. And we will build from CBOR the script optimized. And now we get another folder in the build. And this again has address, CBOR, Plutus file, policy ID, and everything. So these two steps, just Plutonomy CLI and uplc build, will give you an optimized script that's much smaller. Another way to optimize is using Heavy. Heavy is a variant of OpShin, So it's also a Python smart contract language, but it restricts you to functional programming. To use it, we'll first just pip install heavy. There we go. And then replace OpShin by heavy. Let's try and build this. And we get an assertion error. We cannot assign a value to variable res in this line because it was already assigned before. And that's the functional programming part of heavy. We cannot reassign variables. They're assigned once and then are immutable. That's functional programming. So to solve this, we could rewrite this function into a recursive function, or we actually use Python built-in tools that just do exactly this. We're just gonna say res equals datum.beneficiary in context.takeinfo.signatories, and in does exactly what we did before. It loops over this and checks if the beneficiary is contained. So let's try to build this. That worked. And the benefit of restricting ourselves to this functional programming style is that we get an even smaller contract. So without any optimizations, mind that, we are already down at 2 kilobytes. And then again, we can optimize using the default optimizations, and we get another 60% off. So we end up with just a tiny script with 900 bytes size. Coming back to writing complex smart contracts, you might want a bit more complicated logic. For example, we want to have a refund address, and this refund address can always take the funds back from the vesting contract. So we can now check in the validator if the datum.refund address is in the context.takeinfo.signatories. But in this case, we do not want to check for this containment. And we can actually very simply steer the behavior of the contract using the redeemer to check whether it should check the first 2 lines or it should check the last one. Again, redeemers are datums, so we're going to define data class. One of them is the claim redeemer, which we already know from before. This should check the first 2 lines. The second one is a refund redeemer. And if the refund redeemer is passed to the contract, then only the last line should be checked. Now, the redeemer is not unimportant anymore, but it could be either a claim redeemer or a refund redeemer. So union denotes that either of these 2 types could be possible. How do we distinguish the 2 types when we are in the contract? We can use the isInstance for this. So we're gonna ask, is the redeemer an instance of claim redeemer? In this case, execute the first branch. Otherwise, if it is an instance of the refund redeemer, then execute the second branch. And in any other case, just assert false, because this is an invalid redeemer. Let's try to compile this. This works with both heavy and OpShin. We're going to use heavy. Union must combine Plutus data class with unique constructors. So what happens on chain to distinguish these 2 classes is that their constructor ID is checked. This is a static class attribute that we will set to 0 for 1 for the first and to 1 for the second. So whenever we pass a refund redeemer, it will have this variable 1, and otherwise it will have this variable as 0. And the isInstance check here already takes care of for us to check whether it's 1 or 0, and then branch. Let's try to compile. Again, this worked. Nice. Okay. As a final demonstration, I'm going to show you how to parameterize this contract. Potentially, we do not actually want the validator, the user, to be able to define who is the refund pubkey hash. We want to bake this into the contract. So I'm going to remove it from this datum and add it to the front of the validator. So what happens now is this. The validator takes more parameters than what is passed to it on chain. And we can bake this parameter into the contract at the time of compilation. Instead of accessing datum.refund, we're going to access this refund parameter directly. But if we compile the contract, the parameter is not set yet. However, we can call build, here in the terminal again, we can call build. Now, instead of passing, now we can pass in JSON notation the Plutus datum that should be bound to the first argument. If we compile this, it will successfully compile, and if we would have a look at the contract, we would see that it's wrapped into an application where the value we defined here is bound to the first parameter. And now later, executing this on-chain, only the last 3 parameters will be passed. So this is a very simple example on how to bind parameters to the contract. I hope this has whetted your appetite for OpShin and using the toolchain to write and improve your contracts. If you're curious, you can find the project at github.com/opshin or opshin.dev. If you are interested in more examples on how to use OpShin, I recommend to you the OpShin Pioneer program. It's a repository that follows along with the Plutus Pioneer program and posts as a weekly contract written in OpShin instead of Plutus in the Plutus for the Plutus Pioneer program. There's detailed information on how to install and links back to the referred Plutus Pioneer program. So to recap, OpShin is a toolchain but also general purpose Python smart contract language. It interacts frictionless with PyCardano, and it has a lot more tools that are very useful if you develop in any language. So if you are going to develop a smart contract or D-app using any language on Cardano, I recommend to you to check out the OpShin repository.